Alright, now let's jump into the single area open shortest path first, which is OSPF. In this video, I'm going to explain how single area OSPF operates. I'm going to explain the features and characteristics of the OSPF routing protocol and describe the types of the packets used to establish and maintain an OSPF neighbor relationship. And I'm also going to explain how OSPF achieve convergence. Okay, so let's look at the evolutions of OSPF. For the 1988 development work begins on OSPF, which is Open Shortest Path First, and this OSPF is the dynamic routing protocols. 1983, OSPF version 1 was published in RFC 1131, and 1991, OSPF version 2 to support IPv4 introduced in RFC 1247. And the revised version introduces 1998, OSPF version 2 updated in RFC 2328, and the latest one until now, okay, is published in RFC 2740, which is our OSPF version 3 that can support IPv6. Okay, so these are the evolutions of OSPF. Now, what is the features of OSPF? If you look at the OSPF version 2, it supports the MD5 and SHA authentication. However, for the version 3, it uses the IPsec for the authentication. That means this is more secure. And this OSPF also supports a hierarchical design system through the use of areas. Okay, so all these are the OSPF features. You have classless, support the classless address, more secure, okay, due to the IPsec for authentication. And if you are using the version 2, which is IPv4, it's actually support MD5 encryption and SHA authentication. And OSPF also scalable, very fast convergence, and very efficient, okay, because it's only triggered the routing updates when there is a routing change. So OSPF uses the Dijkstra shortest path SPF algorithm to choose the best path to reach to the destination. And Administrative distance, which is AD, is used to determine what route gets installed in the routing table when the route is learned from multiple sources. So of course, the lowest administrative distance is the one added into the routing table. So by default, OSPF configured as the administrative distance of 110. Okay, this will be the focus on our topics today. Okay, what are the components of OSPF? Now, if you look at the OSPF, they will have storing the table, okay, which is the neighbor table, and it's stored into the adjacency database. So inside this adjacency database, it will list all the neighbors routers to which a router has established bidirectional communication. And it's also stored a unit for each router, okay, if viewed using the show IP OSPF neighbor command. So if you want to look at what is actually the information stored into the database, adjacency of the database, which is your table for your neighbor, you can show the IP OSPF neighbor, this command. Okay, next, for the link state database, we call it LSDB. Now, this LSDB is actually storing a topology table. This topology table will list all the information about other routers, represent the network topology, contain the same link state database as all other routers in the same area, and you can check using show IP OSPF database if you want to check for this topology table. And the last one, we will have the forwarding database, which is storing in the routing table. So this routing table will list routes generated when the SPF algorithm is run on the link state database. It is unique to each other and contain information on how and where to send the packets destined for the remote networks. And you can view the show IP route, okay, to view your routing table. So OSPF packet types such as hello, database description, link state request, link state updates, link state acknowledgement. These are the types of the OSPF packet types. Okay, now how does the link stack operation? If you look at the first one, each router will going to send a hello packets to the established neighbor adjacency. For example, R1 send the hello packets to the established neighbors to R2, send hello to R3, send hello packets to R4. Now, when every of the router, assuming that R4 receive it, it will use the link stack advertisement to flood the area with cost and stack of the links. So each router will build a topology table, which is all filled up inside here. Okay, inside your topology table of the LSDB, link stack database, and each router will run the SPF algorithm resulting in the SPF tree. After that, each router builds a routing table that includes the path, which is the shortest path to get to the distant network, destination network, with the complete of your cost metric, okay, to get there. Okay, now let's talk about the single area OSPF. Single area OSPF is all the router contains on one area. Like for example, all this router is contains in one area called the backbone area and known as the area 0. Okay, when you configure it, you can configure it as an area 0. So this area 0 is by default is using a single area and use it in the smaller networks with a few routers. However, if you have the multi-area OSPF, this is how it looks like. You will have the area 0 configured communications between router 1 and router 2, and this will be the area 1. Okay, we have 4 routers communicate with each other, and you have the area 51 and so on. Okay, all these, if you have more than one area, this is called multi-area OSPF. And this multi-area OSPF designed using a hierarchical scheme and all connects to the area 0, which is, this is your backbone. Okay, all your multi-area connected to your backbone, and more commonly seen with numerous areas around area 0, like a daisy or ester. Routers that connect area 0 to another area is known as the area border router. That means this router 1 is the area border router because it's connect from area 1 to area 0. Okay, this is called ABR. Or this router 2 also is the ABR, area border router, because it is the communication link from area 0 to area 51. So any router in charge to communicate, okay, to provide a link from one area to another area, that router is called area border router. Okay, it's used to in the large networks, and multiple areas reduce the processing and memory overhead. And because of that, if let's say this router failure, okay, breakdown in one area, it does not affect other area of area 0 and area 1. So it only affects any area in this 51. Okay, so that's a good thing about multi-area OSPF. Okay, so let's talk about the encapsulating of the OSPF messages. Now, OSPF version 3, which is support the IPv6, also has a similar packet types. Ospf V3 version 3 also will have the hello packets to discover the network neighbors and builds the adjacency between them. And Ospf V3 also will have the database description. Okay, check the database synchronization. Also have the link stack request. It will request the specific link stack records from router to router. Ospf V3 also will have a link stack updates, which is send specifically requested link stack records. And the last one will have a link stack acknowledgement. Okay, it will acknowledge the other packet types if you receive the types of the packets. Okay, so hello packets are used to discover the neighbors, establish the neighbor adjacency, and advertise the parameters. Both routers must agree upon in order to become neighbors and elect the designated router and backup designated router on multi-access networks like Ethernet and frame relay. Of course, it's not the serial point-to-point links. So that's why you need to have a hello packets. Okay. So again, the hello packets is to become enables, you need to do the elections for a DR and BDR. So DR will be stand for designated router, and BDR is the backup designated router. So the type of the field number 1, okay, this type number 1 here is represent the hello packets. If this type change to number 2, it will stand for the database, okay, DBD. And if these types change to number 3, it will carry the LSR, link stat request. Or if this type change to number 5, it is carry the link stat updates. Or maybe you will have a link stat acknowledgement as well, okay? Sorry, the link stat updates is number 4. If the types here is number 4, but then if this type here change to number 5, so you will have a link stat acknowledgement. Okay. All right. So hello interval is how often a router sends a hello packet. Maybe between 14 seconds or 15 seconds. That is your hello interval, meaning of hello interval. Okay. Router priority by default is 1. The maximum will be 255. Okay, with the higher number influencing the DR and BDR election process. So if you set it higher, so the election will be the DR. Okay, so DR means that it will look at the highest priority of your the router priority. Okay, next about the dead interval. Now this dead interval is to determine how long a router waits to hear from the neighbor router before declaring the router out of service. Okay, so you have a DR, okay, which is the designated router, and you have the backup designated router, BDR, contains the router ID for the DR and BDR, and you will have the last list here, which is the list of the neighbors, is the router ID for all adjacent neighbor routers. So all this is the information inside your hello packets. Okay, hello and dead intervals must be the send interval setting on the neighboring routers on the same link, transmitted to multicast address, which is 224.0.0.5 if you are using the IPv4, or if you are using the IPv6, it will transmit to the multicast address of FF02:5, and it sends every 10 seconds by default on multi-access networks like Ethernet and point-to-point links. It means like this topology here. Okay, every 10 seconds, it will send hello packets to the neighbors of router 2, router 3, and router 4. And if you are using the non-broadcast multi-access network, which is like a friend relay, so this duration to send the hello packets will be 30 seconds. Okay, just now the 10 seconds is for a multi-access like Ethernet and point-to-point link, but for a non-broadcast multi-access such as friend relay, is sent every 30 seconds. So dead intervals by default are 4 times the hello interval. Now, if the dead intervals expires before the router receives a hello packet, Ospf will remove that neighbors from its link stat database. The router then floods the LSDB with the info about the down neighbor. Okay, so what does it mean is that, okay, every 10 seconds, R1, we're going to send the packets to the router 2 if this is using a point-to-point link, and times 4, your dead interval will be, if let's say your hello is 10 seconds, your dead interval will be times 4, so you have 40 dead interval. So within the 40 seconds, if router 2 didn't get any reply, okay, to the router 1, so router 2 didn't send any reply to the router 1. Router 1 will assume that router 2 is encountered, it will going to encounter the expired of the dead interval. So the router then will flood the LSDB, okay, which is a link stat database with the info about the down neighbor, okay, to each the rest of the neighbors. Okay, establish the neighbor adjacency. Now, without a pre-configured router ID or loopback address, R1 has a RID of 172.16.5.1. So this is, we assume that for this configuration here, we have the R1. And the R1 is using the router ID of 172.16.5.1. And the router 2 here is configured as the router ID of 172.16.5.2. Now, when your down stat, you configure it, okay, in the initial stat. And what happened to the router is that it will going to send the hello message to the enable, and you say, hello, my router ID is 172.16.5.1. Is there anyone else on this link? You will going to multicast it to the 224.0.0.5 address. Now, when the other side of the enable, which is the router 2, receive the hello message from the router 1, okay, so the router 2 will reply, okay, using the hello, my router is introduced, its own router ID with the 172.16.5.2 and the neighbor list. You were going to send it to the neighbor list and unicast it to 172.16.5.1, okay. So after that, the R1 neighbor list will have the 172.16.5.2, which is the interface of the G0/0. So these are the two-way stat exchange. Then they will update into the routing table. Now, R1 has a default priority of 1 and the second highest router ID. So in this case, it will be the BDR. The reason is because R1 router ID will be 172.16.5.1. Compared with the router 2, the router ID is 172.16.5.2. So the router ID will be based on the highest router ID selection to become the designated router. So in this case, router 2 will be the designated router with the highest numbers, and the second highest will be the BDR, which is the router 1. Okay, now why have a DR and BDR election? Okay, the first reason is because it's going to reduce the number of link stat advertisements sent. The DR, which is a designated router, is the only router used to send link stat advertisement for the shared network. That means you don't have to allow all the routers send the link stat advertisement. Okay, so you try to reduce it. That's why you need to have a DR and BDR election, especially in a multi-access network. In this topology here, this is the examples of the multi-access network. Okay, and the second purpose is to reduce the number of adjacency over a multi-access network. Okay, so there's two reasons why you need to do the election for DR and BDR. And again, how to do the election? The router will going to base on the highest router ID. Okay, that's the first condition to do these elections. Okay, how do we know that how many adjacency will form by each of the router? Assuming that in this topology here, we have 1, 2, 3, 4, 5 router. So with these 5 routers, the formula is you will have a 5 adjacency. You pick up this formula, okay, if you have the 5 router. So 5 minus 1 will be 4, okay, and divide by 2. Okay, so you have 5 minus 1 is 4. 4 times 5, you have 20. 20 divided by 2, you will get 10. So this 10 is represent a 10 line, okay, for you to form the adjacency if you have 5 routers. That means the 10 cables will be needed, okay, to connect to each of the routers for the router 1, router 2, router 3, router 4, and router 5. Now, same goes to the next. If you have the 10 routers, okay, if you have the 10 routers, you use this formula, you will have a 45 adjacency. It means 45 lines connected for the overall of the topology with the 10 routers. So this is what it means by a number of adjacency, okay, in the multi-access network. Okay, the second section, I'm going to explain about the varieties of the spanning tree protocols. So it's implement single area OSPF version 2, configure and on the OSPF router 2 router ID, configure a single area OSPF version 2, explain how OSPF uses the cost to determine the best path, and verify the area's OSPF version 2. Okay, let's continue to single area OSPF version 2. Now in this topic, I'm going to explain about the single area OSPF version 2, configure an OSPF router ID. I'm going to configure a single area OSPF version 2. I'm also going to explain how OSPF uses the cost to determine the best path to reach the destination, and how are we going to verify a single area OSPF version 2. So topology used to describe the OSPF configuration will be shown here. Okay, these are the topologies. This is the topology used to describe the OSPF configuration. OSPF version 2 configuration uses the router OSPF configuration mod. Now from the global configuration mod, you have to type router OSPF and the process ID to enter the command. For examples, if you want to configure the OSPF version 2, you have to start with the router OSPF. And this number is represent the process ID. Okay, so process ID can be any number, start from 1 until a few thousand, or any numbers to enter to this router OSPF command. Okay. Router ID are used to uniquely identify an OSPF router. So we need to understand what is the router ID. So the router IDs are 32 bits long in both OSPF version 2 and OSPF version 3, which support IPv6. Used to in the elections of the designated router if a priority number is not configured. So ways a router gets a router ID. Okay, first you configure using the router ID, which is a RID OSPF router configuration mod command. So if your router ID explicitly configured yes, then you use that as the router ID. But if you don't configure your router ID, the router will going to choose the IPv4 loopback interface configured. So if you don't configure the loopback address also, the router will going to choose highest active configure IPv4. Okay, but normally this one will not be recommended. Okay, because if the interface with the highest IPv4 address goes down, the router ID selection process will start all over again. Okay. Alright, so this is how if a loopback address is used, now do not route this network using a network statement. So router ID will based on the field selection here to determine who is the DR, who is the BDR, and so on. Okay, so again I repeat, DR will based on the highest router ID configured. So if you have the router 1, okay, you have the router 1 with the router ID of 1.1.1.1, and you have another router with the router ID of 2.2.2.2. Okay, so the router ID will pick up the highest router ID, okay, to as a DR. So router ID will be chosen. But if there is no router ID being configured in your router, so the how to do the second elections is that the router will going to consider the IPv4 loopback address. If there is no loopback address being configured also, then the router will choose the highest active, okay, IPv4 address that being configured. So this is how to determine the DR and BDR. Okay, so use the router ID, which is the IP addresses. Examples like the first one is assuming that my router ID is for the router 1 is 1.1.1.1. So in order for me to configure it, I have to configure the router OSPF, the process ID first, okay, which is 10, assuming that is 10. And only you configure the router ID, okay, with the 1.1.1.1. So this two is the configuration for you to configure the router ID. Now, how do you check? How do you verify your configuration is correct? So you have to show IP protocols. Now, when you show IP protocols, your router ID will preview here. 1.1.1.1. If you forgot to issue this statement, router ID 1.1.1.1, so this answer here will not go into preview when you show IP protocols. Okay, so remember that show IP protocols is the command for you to see what is your router ID numbers, okay, the IP addresses for router ID. Okay, so once you want to modify your router ID, okay, assume that your original router ID is 192.168.10.5 and you would like to change it to the router ID of 1.1.1.1. Now, don't forget, once you change it, remember to clear the IP OSPF process, which is this command, okay? To clear the IP OSPF process so that it can refresh it, resend the packets, and after that, you show the IP protocols to verify it again, and this time you should be able to see the letters updated into your routing tables, which is router ID 1.1.1.1. So don't forget to issue this command, to make the router ID change effectively, which is the clear IP OSPF process. Okay, when the older iOS version, which is the Inter-Network Operating System, did not have the router ID OSPF configuration command, so loopback interfaces were used to provide a stable router ID. So for this interface loopback 0, if you configure it as you pick up the loopback 0 as your interface and you have your IP address configured and the subnet mask, okay, this configuration do not advertise this network. It is a common mistake made in OSPF configuration. So do not advertise this network for your interface loopback 0. Okay, once you configure it into your router. So that's just to remind you, when you have your interface loopback 0, please do not advertise this network. Okay. Okay, so next we are going to use the command to specify which interface participate in the OSPF version 2 area. Just now I mentioned already, for if I want to configure it as a router 2 network, to advertise my neighbor, so I have to activate the router OSPF process ID first. Okay, then only I will going to advertise my neighbor, which is the network. Okay, what is your network x.x here is if let's say I wish to broadcast this network. Okay, so I will have 172.16.2.0 and then followed by your wildcard mask. Okay, in this case, my wildcard mask is /24, so it is the inverse of your subnet mask, which is 0.0.0.255, and followed by your area ID. Now, if you are working with the single area, it is configured as the area 0. So for this topic, our focus will be all about the area 0 because we focus on the single area. Okay, how do you determine the wildcard mask? Now, to determine the wildcard mask, you have to subtract the normal mask, which is the 255.255.255.255 with your subnet mask. So a wildcard mask that is with the bit of 0, it will match the bit, and 1 is ignore. Okay, so always remember that the wildcard mask, if 0 means it will match, okay, with your IP address. But if it is 1, which is ignore, okay, this is very easy to remember. 1 is ignore. Okay. Okay, so a wildcard mask is a series of the zeros with the rest of 1. The 0 and 1s are not alternating like an IP address. Assuming that I have a 24 of my subnet mask, how can I get the wildcard mask? So again, you use a full subnet address, which is the 255.255.255.255 minus /24. That means you have 255.255.255.0 when I convert it into the subnet mask. So here, 255 minus 255, you will get 0. Okay, so why is it 3 digit? Because it's 255. So we just make it 0, 0, 0. And then you have 255 minus 255, you will get 0, 0, 0. 255 minus 255, you will get 0, 0, 0. 255 minus 0, 0, 0, you will get 255. Okay, so the answers for this wildcard mask will be 0.0.0.255. Okay, Alright, so next, how if you have 26 masks? So when you have the 26 masks, same thing, you need to use the subtract the normal mask, which is the 255 or 255 or 255 or 255, minus with your 26 masks. So when I convert the 26 ones to the subnet mask, I will get this number, 255 or 255 or 255.192. So 255 for your normal mask minus your subnet mask, you will get this answer, 00000000 and 063. So when you convert it into the decimal, you will get 0.0.0.63. So that will be your wildcard mask. Okay, next, we're going to advertise how are we going to write a network command. Okay, so two ways to use the network command. First is advertise the particular network, calculating the wildcard mask. Okay, in order for you have to advertise it, then you have to calculate the wildcard mask, which is the first method here. So once I have using the router OSPF process ID, I advertise my own network, which is 172.168.1.0. Then you got the 3.0, then you got the 10.4. Okay, assuming that you are in the router 1, so you advertise your own networks here. Okay. Right, so this is the 3 networks. So you can use the traditional method to do that, which is wildcard mask 0.255, this is .3.3, and is configured as area 0. Now, another way, which is much more easier to configure, is to advertise the IP addresses on the router interface with all quote 0, okay, for your wildcard mask. So it means that you don't have to calculate your wildcard mask, which is much more easier to configure. So you can do it in this way. You can modify your configuration command based on this table, and you can just configure router OSPF 10, then network 172.168.1.1, and all these wildcard masks here, you can just by default use it as 0.0.0.0 area 0. Okay, always need to have an area 0 because we are using the single area. But for here, your subnet mask, you do not need to count. So you just need to apply the default subnet mask, which is 0.0.0.0. Okay, talk about the passive interface. Now, when is the time we need to have a passive interface? Okay, very easy for you to identify. When this is your router, by right, the router have to sending the updates information to another router a few seconds. And then maybe when there is a topology change, you have to update again to another router, right? So the router are not communicating with the LAN. This is all the LAN. Okay, maybe you are connecting to your PC, you are connecting to your switch, and so on. So any of the router here with the interface that connecting, not connect to the router, but with another device, so you can passive the interface. So passive interface means that it will going to stop sending the OSPF messages out of that interface. So because of this part here, you don't need to have the latest updates of the OSPF configurations, because your configuration for your OSPF routing messages will only happen from one router to another router. They exchange from router to router, but not router to the end device. So in this case, you have to passive interface the interface that is not using these updates. Okay. So if I'm in the router R1, I'm going to passive this part, which is a G0/0. If I'm in the router R2, I'm going to passive interface of this G0/0 because this one is not connecting to the router anymore. So I don't have to broadcast out my sending updates to this connectivity here. Okay, and also I don't have to passive interface to here. Okay, so that's why is not needed. So the second reason why we need to use a passive interface is it doesn't waste the bandwidth. Okay, you send it out OSPF enabled interface that don't have another router attached. So you are saving the bandwidth usage. Okay, you don't waste your bandwidth. So that's the reason why you need to configure a passive interface. Okay. Okay, next. Okay, how do you use the passive interface command to, so you can just type the word show IP protocols to verify it. Assuming that you already configured the passive interface, for examples, the router one, as I mentioned just now, how to configure it, you can just go back to your router OSPF process ID. Okay, and then after that, you passive interface, the interface that you would like to block. So router 1 is connecting to G0/0, and it is not connecting to any of the router here. So we want to passive G0/0. That's why we have to type the command passive interface gigabit 0/0. So with this, after, how do you verify it is you have to show IP protocols. Now when you show the IP protocols, it will going to show you, okay, this is your passive interface with the G gigabit Ethernet 0/0. Okay, it will preview here if your configuration command is correct. Okay, next, let's talk about the Ospf metric. Now, Ospf is using the metric, the cost as the metric measurement, and it will pick up the lowest path to reach the lowest metric, okay, to reach to the destination. So the Ospf uses the metric with the cost, which is the reference bandwidth, divided by the interface bandwidth. So when you have this formula, it will choose the lowest path to reach to the destination. But the problem now is that there is an issue if you follow by default formula, which is the cost will equivalent to the reference bandwidth divided by your interface bandwidth. So you will get a same result. Your cost will be 1 for even though you are using the 10 gigabits Ethernet. When you apply the same formula, even though you are using the 1 Gbps Ethernet, the cost is still the 1. 100 Mbps Ethernet, the cost is still the 1. So it's not fair, right? Because if you are using the high speed of your 10 gigabit Ethernet, but your metric is still the same with the 100 Mbps Ethernet. So this is an issue because the same cost due to the default reference bandwidth. So you need to adjust this method. So this is by default measurement. Okay, you have 1, and then you have 10, 100, 1000, and so on. So 1 billion here will equal to 90. Okay. Okay, so the cost for a destination network is an accumulative of all the cost values from the source to the destination. So the cost metric can be seen in the routing table as the second number within the bracket. Okay, I think you already learned about this. If this is your bracket, okay, so the first value is called administrative distance, and after the administrative distance, the second value, it is denoted as your cost metric. So your cost metric in this example will be 65. Okay, to reach to the network of 172.16.2.0 from your router R1. So you can also show the IP route, which is 172.16.2.0, to check what is the metric value as well. So here you can also see the result. When you show IP route 172.16.2.0 destination network, it will show you the metric will be 65 to reach to that network. Okay, so because of just now, we have an issue about 10 gigabit per second. Then we have 1 GB and 100 Mbps. It consumes of the same cost, okay, to reach to the destination. So we need to change the reference bandwidth, okay. But then just bear in mind, the changing of the Ospf reference bandwidth affects only the Ospf calculation used to determine the metric, but not the bandwidth of the interface. So how do you change your auto adjust your reference bandwidth? You can configure with this command, autocost reference bandwidth. Okay, autocost reference bandwidth command to change the Ospf reference bandwidth. The default reference bandwidth is 100 megabit per second. So assuming that you have 100 megabit per second is equivalent to 100 times 10 to the power of 6 bit per second. Okay, so for the bit per second here, so you will have a 100 million, right, for bit per second. Okay, so this is how you're going to adjust your reference bandwidth by typing the cost of the auto cost reference bandwidth by typing this command to auto adjust it manually. So assuming that I'm putting the 1000 command. Okay, so after you have changed, the value will be, the cost will be 10. Okay, same goes to when you are using the 1 GB Ethernet. Okay, so when you use the 1 GB for this, assuming that you are using the SAM to adjust the distinguish between the 100 megabit per second Ethernet and the gigabit Ethernet. So now, by default, we use this autocost reference bandwidth of 1000 command. So we set it to 1000. So when you set it to 1000, it will be adjusted right now. Your 100 megabit per second Ethernet will become 100 cost. And if you use the faster connectivity, which is 1 GB Ethernet, your cost metric will become 10. And if you use the fastest one, which is the 10 GB Ethernet, your metric cost will adjusted to 1. So now this table here will represent much more meaningful info. So you are getting the correct answers right now if you configure it manually. Okay, so if you adjusted with your autocost reference bandwidth with the 1000, so you will get your desirable results. Okay, so after you adjust the reference bandwidth, if you look at the topology again, you can show the IP OSPF interface like R1. Okay, originally R1 is using the 64, but after you adjusted to 1000, so your routing table will straight away auto adjusted and your cost path will become 647. So how you know that? You can just go to the R1, okay, after you adjusted that command, okay, to 1000 of the cost reference bandwidth, you will show IP OSPF interface S0/0/0. So it will preview here. Your cost now will be updated from the 64 to 647. Now, same goes to, you will have another method to show your result, which is the one that just now we mentioned. We go to the show IP route, and then you can route to the specific network, which is you want to see your the metric for this 172.164 and .2.0 destination network. So straight away, the router will show you the OSPF value to reach to this destination is 648 metric. Okay, remember that just now we mentioned the second value in the bracket, it is represent your metric value. Okay, so now it's already been adjusted. So you can just show IP route to check this command. Okay, so the default interface bandwidth defines on an interface do not change the capacity of the interface. So it remind you again, the bandwidth values that you change, it do not change the capacity of the interface. So the bandwidth values defined on the interface are used by the EIGRP and OSPF routing protocols to compute. We just want to calculate the metric only. So if you use by default serial links, the default of your metrics will be 1.544 megabit per second. And that might not be the accurate bandwidth for the transmission rate. So how do you want to get the accurate one? You can just show interfaces command to see your interface bandwidth. For example, so you can show interfaces S0/0/0, then you will get this number, bandwidth 1.544 kilobit per second. And if you want to check the cost, you can show IP OSPF interface serial 0/0/1, the particular interface, and you can see the cost of your metric. Okay, so that is how you're going to check. So you can show interface S0/0/01. Okay, this is to show your bandwidth, and show IP OSPF interface S001 to show your cost. Okay, so this two is a very useful command, okay, for you to verify your configuration. Okay, and just now we mentioned that we can adjust the interface bandwidth, right? So how do you adjust it? You can go to the specific interface. You can just go to, let's say R1 like to have an interface of S001. So this is a R1. So S001 is here. You would like to adjust this bandwidth to 64. Okay, so once you adjust it to 64 kilobit per second, okay, when you show the interface of your serial S0/0/1, the router will preview with the bandwidth 64 kilobit per second, which is correct. It's exactly as what you want. Okay, this is how you show the configuration. And then after that, you can show IP OSPF interface serial 0/0/1 then you will get the calculated path of your course, okay, to reach to the destination. So this is how you check your configuration. Okay, and we have the options to manually setting the Ospf cost. So you can also set it with the value, which is the command for IP Ospf cost value. Okay, IP Ospf, and you can put any value here. Okay, to change your Ospf cost. So the no bandwidth 64, this one, we have to put the word no in front. This is the meaning of we're going to remove this bandwidth 64 and we're going to reconfigure another command to replace it. So in this case, for these examples, we remove the bandwidth of 64 and we reconfigure our configuration for the cost. We manually identify IP Ospf cost, which is we manually identify it is to 15625 value, okay, for this path cost to reach to the destination. So straight away when you type this command, when you show interface S0/0/1, the router will have a calculated and it will straight away update for you. And now you will getting the bandwidth of 1544 kilobit per second. So the cost value will be 15625, which is preview here. Okay, so this is adjusting the interface bandwidth, the way on how do you adjust the interface bandwidth 64, and then after that, this is manually setting the Ospf cost command. So this is just to show you that what is actually the command for you to adjust the bandwidth. Okay, you can just go to the specific bandwidth and just type the word bandwidth something, and this value is the one that you want to set manually. And if you want to set the Ospf cost, so this two is the command for you to do that. Okay, so don't forget. So this two is a different configuration command that you would like to get. Okay. Okay, after you have set, you can show IP Ospf neighbor to verify the router to form which has formed an adjacency with your directly connected router. So if you are from the router 1, you should have 3.3.3.3 as your neighbor. Okay, so and then you have a neighbor ID of 2.2.2. Assuming that router 3 is configured the router ID of 3.3.3, and the router 2 is configured the router ID of 2.2.2.2. Okay, so that's why when from your router 1 perspective, if your configuration everything is correct, when you show the IP Ospf neighbor, it will preview you with these two lines. If any of the line missing, that means that configuration is not getting the latest updates from that network. So you have to do troubleshooting. Okay, so the output of the neighbor ID is represent this one. The neighbor ID is represent the router ID of the neighbor router. Assuming that just now I mentioned for your router ID of your R2. Okay, is 2.2.2.2. So that is the router ID of your neighbor router. And what is the value of PRI? Okay, PRI stands for priority. So the Ospf version true priority of the interface used to determine who is your DR, who is the BDR election process. Okay, so that is what we call PRI, priority. And the indicator for the stat, which is the full and then all that. Full means that the link stat database has the algorithm to execute it, and the number router and the neighbor router and R1 have identical. Okay, have identical LSDB, which is a link stat database. So Ethernet multi-access interfaces may show as two-way if you are using the, if you are not getting the full, but you are getting two-way. So in this case, we will know that you are using the Ethernet multi-access interfaces. Okay, the router should be able to show you this. And the dash in the interfaces that no DR and BDR is required. So for this, can you see the dash here? That means you don't need to have a DR and BDR because this is not connecting to the multi-access network. Okay, and what is the dead time? Now, the dead time is the amount of time remaining before expecting to receive a hello packet, which is we discussed already just now for our dead interval. So this is what we call dead time. And you have the address. So this address here represents the address of your neighbor directly connected interface. So it's not the address for yourself, but it's for your neighbor address, yeah. Okay. And the interface here is represent the interface on the R1, okay, used to form an adjacency with a neighbor router. So that's how to teach you how to show, how to interpret the table when you show IP OSPF neighbor. Okay, how about when you show IP protocols? Now, when you show the IP protocols, you are checking for the routing protocol of your OSPF process ID. You can able to check. So you can just show IP protocols. You can check your OSPF process ID. You can check your router ID as well. You can check what is your routing for the networks, okay, that you configure correctly or not. And you also can check your neighbor gateway, okay, the distance that you are using, what protocol, the protocol that you are using and so on. Okay, so 110 is represent the OSPF. So when you use the OSPF, your administrative distance by default is 110. So you can show all these IP protocols to get all the information that you want. Okay, so if you want to check your ID, okay, for your, what you call that, the OSPF version 2 of your process ID and the router ID as well, you can use the show IP OSPF, okay, for this command to show your process ID and also your router ID. Okay, so this show is very important. Okay, the next show will be, you want to verify your configuration whether it's correct or not. You can show IP OSPF interface. Okay, here, show IP OSPF interface to see the details for every OSPF version 2 enabled. And you can also show IP OSPF interface brief, okay, to see the particular information about the enable interface. Like for example, if you are in the router 1, you want to check the specific interface that connecting to the router 1. So you can just show IP OSPF interface brief. Then it will show you, oh, okay, you have 3 networks connecting to these 3 interface of your router R1. S001, S000, GI00. So all this information is preview for your network and the path cost to reach to the destination of 10.5. And the step will be P2P, is stand for peer-to-peer protocols, and MBRS will be 1/1 and so on. So it will preview everything in details when you show IP OSPF interface brief. Okay, it just show you the active interface that connecting to your router R1. Okay, so we have done the version, OSPF version 2. So here we're going to move on to the single area of OSPF version 3. If you understand about the version 3, it is the same as the version 2, just that this version 3 is support IPv6. Okay, just now the version 2 is to support the IPv4, but for the version 6 here, we call it the OSPF version V3. So I'm going to compare the characteristic and operations of V2 and V3. So every time I talk about the V2, you have to remember that this is referring to IPv4. Okay, OSPF, and when we talk about the OSPF V3 is referring to the IPv6. So again, we're going to configure the single area, how to configure the single area of OSPF V6, okay, V3, sorry, and you have to verify the single area of OSPF V3. Okay, so OSPF V3 is used to exchange IPv6 prefixes and build an IPv6 routing table. So IPv6 builds 3 OSPF table, which is the neighbor table, topology table, and the routing tables. Okay, so you can show IP OSPF neighbor. You can also show the IP OSPF database, and you can show the IP route. Okay, to show all these results. If you show the IP route, you are viewing the routing table. If you show IP OSPF database, you are actually viewing the topology table. And if you show IP OSPF neighbor, you are viewing the neighbor table. Okay, so these 3 important to verify your configuration. Okay, the similarity between the OSPF V2 and V3, both of them are the lean stack routing protocols, and both also using the shortest path first, both also using the cost as a metric calculated, which is using the lowest metrics, which is the lowest cost. And the both use and support two-level hierarchical with areas connecting to area 0. So the area 0 is compulsory, even though you are using the area V2 or V3. So by default, you need to start from the area 0, because area 0 is the backbone for your OSPF areas. So your packet types both use the same hello, BDB, LSR, LSU, and LSSEK, which is the link state acknowledgement. So all also using the same packet types. Neighbor discovery also the same. Transition, they are using the hello packets, okay, to send it to their neighbors. And then they also have the DR and BDR elections, okay, also the same. And the router ID, both uses 32 bits of the router ID determined by the same process. So these are all the similarities between OSPF version 2 and OSPF version 3. If you look at here, not much different, right? Just that maybe one support IPv4, another one support IPv6. Okay, another specific things about good things about the IPv6, which is the OSPF V3, is IPv6 link local addresses. Okay, IPv6 link local addresses can able to help you to enable the device to communicate with other IPv6 enabled devices on the same link and only on that link. But in IPv4, we don't have this. So only the IPv6 link local addresses will have this function. So packets with a source or destination link local address cannot be routed beyond the link from where the packet originated. So just to have a further explanation about the link local. So IPv6 link local address are used to exchange OSPF version 3 messages. Okay, so you have R1 here, you exchange your link local address to the router 2, and the router 2 will have exchange your link local address to the router 1. So they are exchanging the information of the OSPF V3 messages. Now be sure to turn on the IPv6 routing to assign, and if you are using the IPv6 and if you want to configure the any configuration in your router, don't forget about this command, IPv6 unicast routing. Now if you don't have this command for every router, so all this configuration can't support by the router. Okay, so this is the crucial for you to know that every router, if you want to configure OSPF V3, this is a must, IPv6 unicast routing. Okay, so these are the steps to configure the OSPF V3. The first one, enable the IPv6 unicast routing in the global configuration mode, which is IPv6 unicast routing. And this one is optional. You can configure the link local addresses, is optional. The next steps is to configure a 32-bit router ID if you have. Okay, so you can just configure it as a router ID with your ID numbers. And the next steps will be configure the optional routing specifics, such as adjusting the reference bandwidth. So if you like to have auto adjust for your reference bandwidth, then this is optional as well. And this is also the optional. You can configure the OSPF version 3 interface specific settings, such as you can set the interface bandwidth. So all the configuration just now we have learned. All right, and then you can enable the OSPF version 3 routings using this command, IPv6 OSPF area. Okay, so let's move on to the link local addresses. So in order for you to verify the IPv6 addresses on the interface, remember that link local addresses are automatically created when an IPv6 global unicast address is assigned to an interface. However, IPv6 global unicast addresses are not required. So link local addresses are required, okay, for OSPF version 3. Let's configure manually. Cisco routers create a link local addresses using FE80:10. So this is actually your link local. So every time when you do the configuration for IPv6, you can configure manually in your Cisco routers, which is with the FE80:. And prefix, it will based on the questions given. And the EUI's -64 process by manipulating 64 bits of the Ethernet MAC addresses. Okay, this is how you configure your link local addresses. Alright, so once you manually configure it, then you can easily to verify using both of the command. The first command, okay, examples like you already done the configuration. You go to the specific interface G0/0, and then you configure the link local with it, which is the IPv6. Okay, don't forget. If you're using the IPv4, it's just IP address on it. But if you use the IPv6, it's a IPv6 here address, followed by the link local, okay, which is FE@0:1. Okay, this is the address for a link local address, and followed by these keywords, link local. So the moment you do this, you are configuring a link local into the interface gigabit 0/0. Now, same goes to S000. If you can just repeat the command, and S0/0/1. Now, to verify these three commands will have the link local, you can just show IPv6 interface brief. Okay, so if your configuration for these three tag effects, it will preview here G00, S000, and S001. Okay, so you can see these three link local addresses preview when you show IPv6 interface brief. Okay, next is for you to configure the process ID. Okay, you can manually configure it by issuing this command, IPv6 router Ospf, and followed by your process ID. Now, same thing just now when you use the IPv4, we have IP router. Okay, IP router, the process ID. But here, if you want to use the IPv6, you have to configure IPv6, and then you have a router Ospf, followed by the router ID. Sorry, this is a process ID. So use the router ID, okay, to assign the router. To assign the router ID. Let's say I would like to assign my router ID to 1.1.1.1. Okay, so you want to have the election of the DR and BDR, so you can use the router ID. So you can show the configuration command that you have configured by showing show IPv6 protocols. So when you show the IPv6 protocols, it will preview here your router ID will be 1.1.1.1. Okay, and if you want to modify it, it's the same as IPv4. You can just clear your IPv6 Ospf process. Okay, right, and you go to the privilege executive mode and you just clear it. So you can just show your IPv6 protocols. Then you have a 10.1.1.1. Okay, then after that you can just go to IPv6 router Ospf 10. Then you configure it as router ID. So now your original router ID is 10.1.1.1. So if you want to change it to 1.1.1, so you can just go back to your IPv6 router Ospf 10. Make sure this process ID is the same as what you configured earlier on, okay, your process ID. Then after that, you reconfigure it with the word router ID 1.1.1.1. And after that, you can just press N. And if you want to make sure that it tag effects, refresh your previous router ID, make sure you have to do this. Okay, clear IPv6 Ospf process. Now, once you issue this command, when you press Enter, the router will ask you whether you want to reset the selected Ospf version 3 processor. So you should answer yes. Okay, you should answer yes. So this is how you complete the router ID change. So same thing goes to your IPv6 Ospf area. So you can use this command. So once you can go for the specific or IPv6 Ospf 10 area 0, you configure in your interface of 00, S00, and S001. So once you have done, you can just show your configuration, verify it with the show IPv6 Ospf interface brief. Basically, the whole concept is more or less the same. Okay, same as here. It's more or less the same as Ospf version 2, if you realize it. Okay, this is actually the same configuration, just that when you use the IPv4, you just show IP Ospf neighbor. But when you use the IPv6, this is the different only IPv6 Ospf neighbor. So if you understand the concept of our Ospf V2, I believe that this is just very, very simple for you to understand IPv6 because the words similar. Okay, it's the same. So same thing, you can show IPv6 protocols, okay, to verify your configuration of your Ospf version 3. Okay, so this is also the same to verify your configuration for your interface and also your interface. And this is to show your route OSPF. Okay, it's the same as the IPv4 as well. So that's about the OSPF version 3. So conclusion for this single area OSPF, for the previous explanation, I already covered how the single area OSPF operates, and I go through with you how to configure the OSPF version 2 compared with the OSPF version 3. So you can use a lot of, the practical exercises, the lab exercises that I prepared earlier on to you, and you can just practice, okay, using this basic configuration. And please make sure you write the configuration command that you have learned. How do you verify your command? How do you configure? How do you adjust your reference bandwidth? How do you set your network address and all that? Okay, for you to practice to measure your single area OSPF. Okay, I hope you enjoyed this video and all the best to you.